Tēnā koutou katoa. For those who don't know me, I'm David Murdoch. I'm the Dean of the campus here at University of Otago in Christchurch, and it's my job to welcome you all. We've got a great turnout today to the inaugural Professorial lecture by Anthony Butler. So this is a very special Grand Rounds. It's not the normal Grand Rounds. Here we're going to celebrate the new professorial appointment on campus. And in that regard, I would like to extend a warm welcome to family and friends and colleagues of Anthony to this event. So thank you for coming today. And I'm not sure if Ruth Sperring is here, but thank you to Ruth for deviating from the normal Grand Round routine to allow us to have this event now. And I think Anthony, being also a consultant radiologist with the District Health Board, it was important to have it this time to allow staff to come. So thank you to Ruth. These inaugural professorial lectures instill a great deal of pride in deans, because we know how much it takes to actually get to be promoted to professor at the University of Otago, which is, I should say, no mean feat. It really is quite a high bar. And what it requires, for those who don't know, it's some fairly clear criteria. You need to show sustained, outstanding competence in all of teaching, research, and service, as well as sustained, outstanding leadership in at least two of those areas. And leadership in particular is the area that the assessment committees are looking for as a difference from the lesser promotions. And that's looked at as a very rigorous process. Before I invite Anthony to take the podium, I thought I'd just say a few words about his career. Anthony graduated from the Otago Medical School in 1998, and I noticed that he had a couple of summer studentships along the way, both in medical physics, and I guess that's a harbinger of things to come. House surgeon in Hawke's Bay before training as a radiologist here in Christchurch, 2000 to 2005, and during that time taking on additional postgraduate study. Now that's not actually unusual for budding academics. In fact, it's encouraged to take on a higher degree, but I guess the difference with Anthony, it was in the areas of physics and electrical and computer engineering at the University of Canterbury, with a graduate diploma in physics and a PhD in electrical and computer engineering. So a good foundation in physics and bioengineering. Thereafter joined the staff here at University of Otago Christchurch, as well as a consultant for the District Health Board, and I was promoted to Associate Professor in 2013 and Professor this year. And also importantly for the University, in 2014 took on the role of Head of the Department of Radiology, and for the University, like many universities in the world, the departments and head of departments are a really key role for the function of the university. So that's a very valued role to have taken on. In 2007, Anthony also, with his father, established the Mars program, focusing on building Spectral CT systems. Now, I'm going to leave it to Anthony's talk to expand on that, but just needless to say that this has been a very successful program that has grown over time, that has attracted considerable external research funding, including $12 million grant from MB and a member of the NZ MedTech Core. There's also been a lot of commercial interest. Also been a steady stream of postdocs and PhD students, in fact increasing over time, and for a dean that's a little bit anxiety provoking how to accommodate them all, but it's a fairly good problem to have, and a real reflection on the actual program itself and the success of that. Also, it really highlights a very successful collaboration between University of Otago, University of Canterbury. Undoubtedly the family connection helped there, but really that is really the direction of travel that we like to have, and those important relationships with the other partner institutions in Christchurch. Along with this, Anthony started about the same time had a key role in establishing the Centre for Bioengineering and Nanomedicine, and still has a leadership role in that. And for the University of Otago, that's its major footprint in bioengineering, where the centre of gravity is really around Christchurch, in that with Anthony and others. There are a few other distinctions. I won't go through them all, but he's also a research professor in the Department of Physics and Astronomy at the University of Canterbury. And I know it was a semi-finalist, I didn't know this before, with your father, I think, and for the New Zealander of the Year award in 2015 in the area of Innovator of the Year category. So, and also just the last comment I'll make, I was thinking there aren't actually that many professors of radiology in New Zealand, and I just checked with that, I think he's the second, so I think there's only one other radiologist in the country at professorial levels other than Anthony, so it's not and I think that's really consistent with the history, that there haven't been many over time. As your Dean, Anthony, I congratulate you on the promotion and invite you to present your lecture.
So thank you for coming. I'm rather surprised at the size of the audience, but that's very gratifying. Today I'm going to be talking about my Mars research. It's a slightly different lecture than I'd normally do, in that the introduction section has been replaced by a whole lot of my research history that introduces the basic scientific concepts, so I can talk about the Mars program at the end. The other thing is people observed outside. I've done a few other unusual things for myself. One is I've had a haircut. And the second is I've put my qualifications on my talk, which is something I actually, as a person, tend not to do. I perhaps fit more the casual role. So here's the overview of my talk. The first half is I'm calling the journey, and I'll explain the various research projects and activities I've done over the years, and with each one I'll bring out one or two scientific points that are critical for the second half of the talk. The second half of the talk is about New Zealand's Mars Spectral CT program. This involves about 40 people in Christchurch, dozens, literally dozens, about 20 or 30 different international collaborators that we published or have agreements with. And then the last section of that I will talk about why doctors and patients should care about this research. So I'll start with the journey. Way back at medical school, this is me on the right, I went to medical school and I quite enjoyed that, but I had an interest in physics, so part-time I did a few extra physics papers, and as David alluded to, I ended up in radiation oncology. I didn't want to have a real job, so I did 3 summer studentships, and I had the best job title I think I'll ever get, which is casual physicist. What I learnt at that stage, because I was studying X-rays, that X-rays are like visible light. They come in different wavelengths, frequencies, colour or energy. And I'll use those terms interchangeably. Today I'll try and use the word colour, but if I slip up and say energy or frequency, just think colour. Now these are all part of the electromagnetic spectrum. X-rays do many of the things that light does, plus a few others, but if you're thinking about X-rays, you have to think they have colour. These are some of the projects I did as a summer studentship. My first publication was on linear accelerators for oncology, and we actually had to use 2 different X-ray colours, 6MV and 18MV. So even at my first summer project, it was pretty clear to me that colour was important. I did some computer simulations one summer. Again, the X-ray colour comes in, and at one point I did some experiments using a spectroscope that told me the X-ray colours. So the take-home point, and I hope I've nailed it, is X-ray colour is important. I then went off, did a few years as a junior doctor, and ended up in radiology. I quite enjoyed imaging. This is the way I always picture an imaging system in my head. We have an X-ray source, which hasn't really changed since this photo was taken. They now tend to be a beige box rather than a black box, but essentially the same. We have an object that in the hospital we tend to call a patient. We have a detector system, which in this case is a fluorescent screen, so it's probably made of phosphorus. The X-rays hit it, the X-rays glow, and the radiologist, which I call a pattern recognition system, looks at the glowing and says, okay, I can interpret what's going on inside the body. Now, one of the things that was missed in that whole system is the X-rays came in and the phosphor glowed. You have no measurement or idea what X-ray colour was involved. So it's what I call a black and white or a Greyscale system. Around that time, I went to my first international radiology conference, and this is RSNA. They claim it's the world's largest scientific conference, 50,000 attendees in Chicago. They have 2 rugby fields of new technology. And I was doing on call, and I was using these things called CT scanners. They are the workhorse of radiology. Our registrars on call pretty much do CT all evening. These are X-ray systems. So if we look at one of these, a CT works by having an X-ray source, which I introduced on that first diagram, the X-ray beam, and a row of detectors. Now, like those original phosphorus screens, those detectors in that CT there work by glowing. You happen to hook them up to a photodiode couple, but essentially they glow, and so you're again missing that X-ray colour. So these fancy high-end CT scanners are ignoring a whole lot of information that's in the X-ray beam. However, they do give us 3D pictures. So this is a 3D picture of the chest. The person's gone through the scanner, and we can see this person has some abnormality in their lungs, probably a cancer. So what did I learn as a radiology registrar? 3D X-rays are the best. Computed tomography, you want to have a 3D volume rather than just projection. Around that time, radiology changed. In 2005, which is when that picture from RSNA was taken, radiology was absolutely booming. It was growing at about 4.5% a year. Hospitals were spending millions and millions of dollars a year on new equipment, and then it slowed down. What happened? Well, over that period, CT went from a single row of detectors there to multiple rows of detectors. So instead of just having a line, they had an array up to about 6 or 7 centimetres in thickness. Now they fundamentally worked the same way. They just glowed, but they went much, much faster. So this is the sort of image you got. You could get a 3D volume of a whole person in about 2 or 3 seconds. The limiting factor, I'm told these days on a modern CT scanner, if they put the patient through any faster, they'd fly off the end. If you can think of someone lying on a bed and you accelerate them through a donut in 2 seconds, they're moving pretty fast, and you have to take into account the acceleration of the bed while you do the imaging. However, we've got pictures that are still fundamentally Greyscale. Going faster, not much benefit. I can do you in 2 seconds, I can do your heart in 1 beat of the heart, doesn't help. I can image everything down to 0.5 millimetre or even 1/4 millimetre, doesn't help with my diagnosis. So what actually radiologists really want to know is the molecular stuff, the biochemistry stuff. So the idea is to work out what the tissue is, what is its behaviour, is the treatment working? And that means we need to know the constituents such as fat, water, calcium and iron. We want to look for pathogens and cancer labels, so we need physiological markers. So radiologists want molecular information. Gone are the days of radiology being just anatomy. By the time I retire in 25 years, radiology will be close to biochemistry. Now, as David alluded to, partway through my radiology training, I wanted to get back and do a bit more research. I ended up in an electrical engineering department doing something called computational imaging. It was quite fun. It was entirely computer-based. My thesis was entitled Eigenimage Processing of Chest Radiographs. Slightly technical name, but basically that's pattern recognition or computer-aided diagnosis. That falls into the category that's sometimes called artificial intelligence. It's pretty hard to explain quickly, but we were taking a training set and decomposing it using computers. And there are a few things that I want you to learn from my PhD. Firstly, images are just a bunch of numbers. In a scientific sense, you load them onto the computer, they range from -1,000 to +10,000, depending on the image you've got, but they're just numbers. A chest X-ray might be 10 million numbers, 10 megapixels in fact. Most of you might know maths can find patterns in numbers. Simple. And so using computers, we can actually find patterns in numbers or patterns in images that the radiologist will never see. The human eye is trained to do certain things. Computers can be trained to do lots of different things. So using computers can be quite helpful with images. Now, one of the problems, though, is some of the patterns we can find can be really abstract and really hard to understand, and so we have to work out ways to display and interact with them. Some of you may have played with our 3D workstation we have outside, where we have what's called fish tank virtual reality. That's one of the ways to view them. Now, you end up from my PhD, this is one of the diagrams from it, and as I said, it gets abstract. But essentially, these are a three-dimensional diagram, but we were actually looking at a 10-dimensional space, looking at possible patterns of variance, with 1,000 common patterns of variance and one test image. So you can see why you're starting to think 10 million dimensions, I need a computer. However, the only thing I want you to remember from this is maths and computers are needed to understand and display X-rays. That's the only point that most people need to understand. So I finished my radiology, went on a 6-week holiday with my family, my wife and my one child at the time, to Europe, and we met my father there for 2 weeks and travelled around Croatia. One of the things, my father was a professor of physics, so when you go on holiday with him, you occasionally talk about physics. And he was working at the time, he's in the physics department at Canterbury, he'd joined up with CERN in the year 2000, I hadn't really paid any attention, this is what he did. And he was saying to me, you should go and talk to some of these guys here about some of their detectors. So at the end of my holiday, I went to Geneva. This is where CERN is, it's actually this little campus here. This is your accelerator called the Large Hadron Collider. It's a 27 kilometre circumference accelerator. The one I'd used in radiation oncology was about 1 metre, maybe 2.5 metres. So 27 kilometres was quite impressive. They've done a few important things. They would claim the most important things that they did is discover the Higgs boson. For most people, I think the most important thing they've done is the World Wide Web. So these are some of the detectors. Dad and I actually still work on CERN technology. We're still part of the CMS experiment. This experiment is one of 2 experiments that was built to find the Higgs boson. This is myself and my father beside the accelerator, and this is me beside this CMS. It's called the compact muon solenoid. It's 12,000 tonnes, not 1,200, 12,000 tonnes. It's 15 metres diameter, it's 21.5 metres long, and it's 100 metres underground. By compact, what they actually mean is it's so tightly packed in, you cannot get your hand into any part of it. It's basically a solid bit of electronics and detectors. Within the middle of that, they had a new type of detector they called photon counting detectors. So this sits right in the middle there. This is the so-called silicon barrel. They're basically an array of microchips stuck in the middle. So out of this work, I managed to get my most cited paper. 12,000, or nearly 13,000 citations last time I checked. The only problem is it's got 4,000 authors. So it's almost three and a bit citations per author. But it's still great to be part of that collaboration. And actually one of the most important parts of that, of course, is it really does highlight something that's going to become apparent when I talk about Mars. All good science, well, not all good science, a lot of good science that is done these days is done part of collaborations. Most research projects I've had or I've worked on have actually come by talking to people. I don't know many scientists who would claim they had an idea on them by themselves. Almost every scientist I know would say, I had an idea when I was talking to that person, or we had an idea talking together. And I think that is an important point for people to realise about science. Now, Dad at that stage was actually involved in the Medipix collaboration. He sent a master's student off. And so on my first visit, I actually met the head of the Medipix collaboration. This is a bunch of universities which are trying to turn some of that detector technology and make it suitable for medicine. The collaboration's been running for over 20 years, since the mid-90s. Canterbury University has been part of Medipix 3 and now Medipix 4. It's got at least 25 universities. Medipix 3 had 22, and they're universities you might have heard of, such as Oxford, Cambridge, Berkeley, Stanford, etc. And in fact, this is a collaboration meeting I attended, and in fact Nigel Anderson attended with me in Prague. There were over 110 people at that collaboration meeting alone. If you know about how scientific conferences work, that means the collaboration probably has 200 active scientists in it at any one time. This was the detector I got most involved with. Around 2006, 2007, I was communicating very frequently with the designers of this detector, spending quite a lot of time at CERN. This is a spectroscope. This is a circuit diagram of a spectral X-ray detector. It's 110 micron diameter, or edge, which means on this bit of silicon, there's 16,000 detectors. And you can measure up to 8 X-ray colours at once. It's actually quite clever in terms of electronics. There's 4,500 transistors in that detector, and half of them are analog and half of them are digital, which makes life really complex for the engineers. And actually they all communicate with each other. So for those of you who are interested in computing, this is actually like having 16,000 mini computers all talking to each other. It's quite challenging. And you compare that to the original spectroscope I was using as a medical student. This had a single 30 millimeter detector. It could do up to 128 colours at once, so that was quite clever. Unfortunately, it required a trolley of electronics beside it, and you had to pour liquid nitrogen on it to keep it working. So it was a little less practical. Whereas here, you've got a detector in silicon, or 16,000 detectors in silicon. And that means you could do colour imaging. So this is a colour X-ray that was obtained here in Christchurch Hospital around 2006 or 7. It's 14 by 14 millimetres, it's a fetal hand, and we use 4 X-ray colours. So when I was a medical student, something like that was completely impossible. You kind of knew the physics said you should be able to, it was there, but the engineering wasn't in place to actually measure it. So my take home from that is CERN made colour X-ray imaging possible, and I think that's very nice. So that's the end of the journey. These are the take-home messages I want you to remember into the second half of the talk. Radiologists want molecular information. We want to get more out of the data. X-ray colour is important. Hopefully I've made that point. CERN has made X-ray colour imaging possible, so it's now a reality as opposed to something that might happen. 3D X-rays are best, so we don't want a 2D picture like that fetal hand, we want a 3D picture. And to do all of this, we're going to need to use maths and computers. So that now leads me on to talking about the Mars Spectral CT program. So the goal of this program is to find out new information about tissues. We've now got a new tool, a new ruler as someone might say, to look at tissues. But we don't actually know what it means or how to interpret it or how to use it. But we want to get as much of that out and understand it. We also want to have a route to human imaging. Being a clinician, one of the most important things about discoveries like this or programs like this is you actually want to get it into the clinic, which means we need to go from working on a lab bench of a physicist into something that's practical for a hospital. We've been very lucky, and I'll just credit it here. We've been funded by Ministry of Business in its previous incarnations to the tune of about 20 million. We've got a spin-out company from the University of Canterbury, and my disclosure is and most of the scientists are shareholders in that, and that's gone through the process of various fundraising rounds, including successfully seeking venture capital. We have a lot of support from the universities, which is very pleasing, and we've had support from health organisations such as the National Heart Foundation and the Arthritis Society. So the team is about 40 people in Christchurch. It's always very hard to measure a research team. There's some people working full-time, and there's actually, particularly in the medical school, a lot of people who are not specifically working on Mars, but are using it as a tool for their research. We have 4 universities in New Zealand involved. We've got a lot of international partners, such as CERN, Mayo Clinic, I'll talk about them in a moment, and other significant universities. We also have a partnership agreement with GE Healthcare. They claim to be the world's largest engineering firm. I suspect Tata from India is chasing them as hard as they can. And perhaps the most gratifying thing for me, I only read this from a document from one of our team, we've actually just reached the point of having 30 current or completed PhD students. And as someone who's been involved with education, that's actually really a career highlight for me at this stage. So I said spectral CT is now possible. We called our system Mars. It sounds futuristic. It's easy to spell. It kind of aligns with CT, MRI and PET in terms of short, catchy words. And it also provides lots of opportunities for puns and jokes and talks and journal articles and things. We've called it an all-resolution system because when we talk about an image, we have to talk about the energy resolution or the colour of it. We have to talk about the spatial resolution, i.e. how big is something or where is something. And we have to talk about the temporal resolution, so when did it occur? You know, what phase of the heartbeat is that image in? Now, if we compare that back to a standard CT where you've only got the Greyscale, you've only got spatial and temporal resolution. This is a physics student with one of the early scanners, and I'll talk more about the progression of our scanners. Just to recap on CT, this is a sort of summary diagram, I guess, at this stage. This is the way I tend to think of CT. You have an X-ray source putting out a range of colours, wavelengths, frequencies, energies, passing through a patient, they're attenuated, you have a Greyscale detector that glows, and from that you calculate the Hounsfield unit in 3D. Christchurch Hospital bought a dual energy scanner a few years ago. It works by having two X-ray sources, putting out slightly different X-ray energies. They're both attenuated in the patient, and then you have two sets of Greyscale detectors and you get 2 points on the attenuation curve. This is what I would call spectral CT, where you have a single source putting out a wide range of colours. They're all attenuated, and you have a colour detector, and then you get multiple points on the attenuation curve. So this is like moving from black and white film to colour film. So why is that useful? Give us some examples. This is some work that was done 2009 and 10, I think, where we just tried to see, well, can we see anything different using colour that we couldn't otherwise see? And so we thought about things like iodine, barium, gadolinium. These are used quite frequently in radiology. And we realised if we could see them and identify them as individual components, we could start to use them in combination, and it would open the door for new pharmaceuticals. So we took a mouse and we put iodine into its pulmonary circulation, we put barium into its lungs, and then we have calcium. And of course, all of these things show up white on a black and white X-ray. So that I know is iodine because it's in the circulatory system. Somewhere in there is the barium in the lungs. It's a bit hard to tell which is heart and which is lungs. The bone's white and the soft tissue's grey. And if you do a traditional CT, it looks like that. You could probably adjust the shading and pick a few more things out. This is a colour CT of that same animal. Okay, so I've used pseudo colour to the various materials because we don't. You have to translate, if you like, from where they are on the electromagnetic spectrum out at the high energies of X-rays down to something sensible, and we tend to assign a colour based on the material. I'll talk a bit more about that in a moment. So here I can see we've got iodine in the pulmonary circulation, barium in the lungs. I can see the soft tissues is a different colour and the bone is a different colour. And we actually have a tool with what we call a magic lens, so you can just pick out a small region. Of course, if you can take a 2D picture, you can make it into a 3D picture, you can rotate it round, you can look through it. So those of you who are familiar with anatomy can probably pick out various lobes. You can see the barium kind of scattered through the lungs, and although you can see the iodine in the right ventricle, and it sort of ended up squirting back through bits of the lungs as well, bits of the pulmonary circulation. So 3D images using computers. So our scanners. This is Mars CT1. This is my favourite one. And that's because I spent many, many hours on this. It was built by the physics department at Canterbury University and with the electronics done by the electronics department. And it worked. It was a physics experiment. X-ray tube in there. If you look on the mechanics, the X-ray detectors at the back. It was hooked up to a computer, and it was all command line driven, and it was a bit awkward. We then made a version 2. It looked a bit neater. We put in a steel box as opposed to lead ply. This is the one we brought across the medical school. It went into the basement, actually right behind where you guys are sitting. Same principles in that we have an X-ray tube, the Medipix detector at the back, and that's actually part of my lunch. That's an apple core wrapped in Glad wrap with a twist tie around it. I didn't have a suitable object image, and it seemed to work. V3 we built several of, and you can see my father again here. Him and I Together we took that to the Mayo Clinic. We've got colleagues there who do cardiac research, and this is unpacking it in the basement of Mayo. We built several more. They went round to places like Germany and Russia and a couple more to the US. These were sold to people who wanted to do CT research. People who said, I want to be the first person in the world to understand what I can do with this sort of technology. More recently, we've got what we call a commercial system. The two big changes from those earlier systems is that these are human ready. So for the last 3 years, we've been putting all of our technical efforts into making the scanner human compatible. We've changed our X-ray energies from the low energies that you might use on a mouse to the high energies you might use on a human. And we tried to make it easy for biomedical users, so you push literally it's a green button and the scanner auto-configures itself. You can put the object in. A mouse takes about 8 minutes to scan, and about an hour later you can sit down on a workstation and look at the data. CT1, that first picture I showed, took an afternoon to get the scanner prepared for the scan. Might take 24, 48 hours to scan your mouse, which had to be dead, of course, if you're going to do that, and then a month to get your data back. So we were a little bit slow at that stage. We've got one here in the med school in one of the labs. We've got one in upstate New York, Rensselaer Polytech, and one at Notre Dame. And I actually heard last week the one at Notre Dame took 300 scans in a month. So they're using it fairly heavily. I'm looking forward to finding out what they've done. This is our visualization tool. It's on display outside, and we'll have it there for a bit longer afterwards. It's called Fish Tank VR, so the object sits in front of you, you can manipulate it. We did this in partnership with the HIT lab at Canterbury. Somewhere along the way I actually spent a few years in the HIT lab and learned some of that stuff, but now we've got a team of 5 or 6 people who are in there permanently. This is a commercial release in the Notre Dame lab, so you can see the scanner. We sometimes refer to it as a barbecue. You lift the lid up and you put your sample in, and they've got their workstation sitting right beside it. Here in the med school, we've actually just had to have 2 workstations, are fairly heavily used. We keep them on a different floor than where the scanner is. So why would people care about this? In particular, why should patients and doctors care that we can do this? We went from Greyscale to material imaging. So this is a phantom here. By phantom I mean it's a perspex block with little tubes, sellotaped onto the outside probably, containing various materials: calcium, gadolinium, iodine, gold, water, fat. Okay, on a Greyscale image they all look roughly the same, and in fact if I adjust the concentrations of them they will look identical. On a colour image, you can use that X-ray colour to tell which one's which, and you can work out the concentration of them. So we can see the gold here is at 4 milligrams per mil, 8 milligrams per mil, 9 milligrams per mil, etc. So you've got quantitative imaging, you get the actual number, and material-specific imaging. So if you do a whole mouse, it can look like that. This one's had the water shaded blue, the calcium shaded white. I'm not sure what colours are what, but I can tell this here is kidneys and bladder and bowel and lungs, so this has had contrast agents put in, and of course you can strip even all of the water off and just show certain channels. So you can identify them, you can do a whole mouse, you can do multiple materials simultaneously. And you get, I put this in to show that we have uncertainty, so it's a standard imaging tool. You know, this is how accurately I know each thing, and this shows the concentrations we can get down to. So what clinical projects have we got running at the moment? We have 6 projects running at the moment. We also have a few that are sort of starting up. Each project sort of goes through its phase of acceleration, slow down, acceleration, and I'm constantly looking what more can we add to this list. We've been doing soft tissue quantification. Being in New Zealand, we started with sheep. And in fact, we did this work with Silver Fern Farms, who want to know this information on in their processing factories. We took a bit of meat and we scanned it and we separated out the water, the lipid and the calcium, and they're separate channels, and you've got the concentrations. So if you render them correctly, you can get a 3D picture which looks a little bit like a photo, and you can see the marbling in the meat. So that's kind of cool. Silver Fern Farms were actually delighted at the quality of information we got, and the next question was, we want to do a whole sheep every 3 seconds. Okay, we'll get back to you. but it shows the potential of the technology. You can get this information that can otherwise be very, very difficult to obtain. So we use exactly the same technique on a carotid artery. So this is the artery in someone's neck. This particular patient had come in to the hospital with a mini stroke or a TIA, and they would have had an ordinary CT to look for a bleed, and then they would have had an ultrasound and decided there's a narrowing in the neck, and they would have had that taken out. And so we've taken it from the operating theatre into the medical school, and we've scanned it. We've done dozens of these now, I'm not sure, 80 perhaps. And this has a lipid-rich core. We can see the bifurcation, we can see the calcification. We can render it in 3D. You can see again the necrotic core. So just using the intrinsic tissue characterization, you get more information about the object than you would on a grayscale image. And so that's really interesting to follow. And although in this case we've looked at atheromas, just about any part of the body has different amounts of fat, water and calcium, and we haven't looked at them yet. We started working with the orthopaedic group on osteoarthritis quite a long time ago, in fact, and this person has had their knee removed for a knee replacement. This is I think must be the lateral half of the knee. The medial half of the knee had really bad osteoarthritis, the cartilage completely eroded. This half, the cartilage is of normal thickness, but by introducing a contrast agent to the knee, and in this case the knee had come out, so we did it in a petri dish, we can see the biochemical changes of osteoarthritis before you see the morphological changes, before you get thinning of the cartilage. So that's kind of interesting if you can do it in a petri dish. I quite like to do it before I take the knee out. And it starts to enable medical researchers to say, okay, we've got the biochemistry, we've now got a test to monitor progression of disease, which means that developing drugs are going to be much easier. Instead of having to rely on the patient saying, my knee's hurting, my knee's not hurting, we can actually measure the biochemical changes as the osteoarthritis evolves. So work to be done, but we've got it to the point of proof of concept. That research, that clinical research, I think is going to go on for the next 10 or 15 years in this field alone. I said we could get structure and function at the same time. This is from another couple of PhD students. They took some human tibias, actually sheep tibia there, they've also done human, and we look at the structure of the bone. We can see the little holes and what are called trabeculi, the walls, quite nicely. We can see them down at a few hundred micron, but we also get the calcium density. So in the same time, you're getting bone structure and bone mineralization. Now, when you have a disease like rheumatoid arthritis or osteoporosis, you get different amounts of bone resorption and loss of mineralization. So being able to characterize those is kind of useful. And in therapy, when you give people things like bisphosphonates, you may change the mineralization before you change the structure. So being able to measure them simultaneously will enable a whole new type of research to be done. We started looking at cancer imaging. I think cancer imaging is very important. About 35% of New Zealanders die of cancer off the top of my head, a lot. This mouse, we put some gold nanoprobes in. We also gave it lung cancer. We gave it lung cancer on its back. And then we injected these probes, and these probes targeted the cancer. Okay? It takes about 24 hours for the probe to accumulate in the periphery of the tumour, but it means we can see where it is. And in fact, these particular probes just measure vascularity. They measure how permeable the blood vessels are, which is one of the reasons it tends to collect in the kidneys and in fact the liver as well. We then moved on and started doing specific probes. So in this case, we've taken Raji cells from a cancer, and we've got gold nanoparticles, some of which are attached to rituximab and some attached to Herceptin. The Raji cells only bind to rituximab and they light up. These are our various calibrations and controls. So that's saying this cell pellet here, we know there are Raji cells in it because we've used a specific label. So think about this in future. When someone presents with, in this case I guess, breast cancer, you can start to use radiographic contrast agents that you inject, which will tell you what cell lines are in which part of the tumour. And as you treat the tumour, you'll be able to see which cell lines are dying off. Okay, we're still at the stage of doing it in a petri dish. There's an awful lot of research to go. Again, I'd say decades before this is well understood. This is a sort of proof of concept. There's going to be dozens and dozens of these nanoprobes made, but we now have an imaging tool that can do it. We've started looking at reducing metal artefacts in bone. One of the problems with putting metal into bone, say in a hip implant, is metal has its own X-ray colour, and so you get a lot of artefact off it. The radiologists call it beam hardening. What that actually means is the beam has changed its colour and become higher energy. And if you're measuring the X-ray energy, X-ray colour, you can correct for it. And even just narrowing the bins down to make it more specific to one energy gets rid of it. So this is a standard CT of a orthopaedic screw in a bone, and then you do a Mars image, and you can see on the standard CT you get this black appearing here, that's beam hardening. You get artefacts off the metal, and by measuring the energy information you get rid of that, and you get to see where the metal is. And so of course we highlight it there. One of the other projects we've got running is looking at metallic scaffolds. So a lot of implants, so hip implants and knee implants, for example, that are done, no longer use cement. They use a porous scaffold where the bone grows through into the implant and sort of fuses. If you're developing these scaffolds, you want to know how fast that bone's growing in. It will depend on what the scaffold's made out of, what surface it's got, how rough it is, the size of the pores, but actually being able to measure over time that ingrowth is kind of helpful. So that's why the researchers want it. When we can start doing that in a live person and someone presents with a sore hip implant, you could potentially do a scan like this and go, oh, it hasn't fused properly. I know what's going on. So you end up with more information. I made a video of this one many years ago as well. So that's the scaffold. And you can see it's holy. That's the bone. And the trick is these have actually been scanned at the same time. That's just the bone component. And I'll show you they've been scanned at the same time because that's the bone ingrowth into the scaffold. Okay, so that's what I mean. We can separate them out as separate channels, but they're actually a single data set acquired at the same time. So that's a sheep bone. And as you can tell, that had to be removed from the sheep to do that image, unfortunately. Just have to wait for it to finish or it won't move on. We've also looked at gout. Dual energy has been used for gout for a while. This person had their finger amputated because of pain from the gout, and you can see the gout crystals and some erosions. When we put it in the Mars scanner, we get better energy information than you do off a dual energy system because we've got more energy bins and better energy resolution, and we have better spatial resolution as well, so we can see the microcrystals that you couldn't otherwise see. One of the big things that's important, of course, with X-rays is X-ray dose. How much many X-rays are we going to put into the patient? We've been working with Lausanne Hospital on measuring these X-ray dose. So this mouse has little things called TLDs inserted all the way through it to measure X-ray dose. We put in some contrast agent to make it a real scan, and we scan this and measure the dose. In fact, we did it many times, of course, and we know that the dose of our system is sitting at about the same as any other preclinical scanner. So current work and next step, and there'll be time for questions, so I'm pleased about that. We're taking Mars to humans. We have to go from imaging a small object like that to imaging a large object like a foot. We built up this gantry. It's not a traditional CT scanner, it's an experimental gantry in that we have an X-ray tube there and we can put a detector on there. It's kind of open so you can replace the detector easily, go for bigger arrays. You can adjust the magnification by bringing things in and out. You can adjust the speed of rotation and the speed you're putting patients through, but we're doing human scale. This is the sort of technology that's involved in doing that. This is one of our Mars cameras. These are the Medipix chips. They have a semiconductor on there that stops high energy or very high, very blue, I guess is the right answer, coloured stuff. These are then fed into individual circuits. For each detector, we have to have a separate computer, and then we have an Ethernet switch. So a camera like that is literally hand-built, and I did see Brian round somewhere, who probably, there he is, who built this one. And there's a huge amount of engineering. 5 computers in the camera, 2 control computers, and 2 single board computers. So this scanner would have 9 computers in it in a box this size. As we move to a human scanner, we might end up with 50 detectors. So we've got 50 computers to control, all reading data as fast as they can. So why are we doing this? Why did the government give us money to do this? Our goal is to grow, well, the government's goal is to grow the New Zealand spectral CT industry. Did anyone here know that New Zealand had a spectral CT industry? Well, the government now believes we do. And so they're funding this research to try and grow the skill base and the technology and the infrastructure for this. And we're funded up to our first clinical trial. So the first human we put in will be a success for that program. And our goal is to assist other New Zealand medical technology companies. So the scaffold I showed you was, I think, from a local company called OSIS. We work with companies like Boutique Nanoparticles from Wellington. And we work with other groups such as local electronics and mechanical groups. So the next step before questions. So for the next 12 months, I'm actually full-time on Mars. One of the nice things about working for a university is you get research and study leave, and mine actually starts today at 5 o'clock. It's just luck that it happened to coincide with this. So I thought I'd elucidate what I'm planning to do on that. The first thing is to finalise the machines for human studies. I think we're fairly close. I'm going to get more involved, and you know, this is a team of 40 people, so when I say it's the team's doing this. We need to keep expanding the list of biomedical uses. We haven't even scratched the surface of it. This is one of the reasons why we've been forming so many international collaborations. We need as many people to look at as many applications as possible. Not everything's beneficial. The problem is, what happens is one bit looks beneficial for a while, you go a long way, then you get stuck, and then 3 years later it accelerates again. So the only way to handle a problem like that is to do lots of things in parallel. I'd like to re-engage in the technical details of this project as well. As I sort of alluded to, for that CT1, I used to know the order of ones and zeros you use to talk to the side of the chip. I don't have that level of detail anymore, and I'm looking forward to that, and I'd like to grow our collaborations both locally and internationally. So thank you, and that leaves about 10-15 minutes for questions.